From the time that we are very young, we learn that the world around us is composed of particles that are too small to be seen with the naked eye. In this video, we will discuss the very small particles that make up atoms. Since the late 1890s, scientists have been able to characterize the particles that are found in atoms. We call these particles subatomic particles. The properties of subatomic particles are completely different from the properties of individual atoms. And understanding these particles and how they form atoms can help us explain many of the phenomena that we observe in nature. We know that every atom contains a nucleus, much like a cell contains a nucleus. The nucleus carries an overall positive charge, but the nucleus itself can actually contain two types of particles, protons and neutrons. Not every atom has neutrons, but every atom has protons. A proton is a positively charged particle with a mass of 1.67262 times 10 to the minus 24th grams. Today, we believe that protons are composed of even smaller particles called quarks that are held together by small springs known as gluons. For the purposes of this course, though, the most important properties of the proton will be its charge, location, and relative mass. You will not need to memorize the actual mass, but you must be able to remember the mass of the proton in comparison to the other subatomic particles. The number of protons in a nucleus is used to identify and name an atom. For example, consider a sample of carbon atoms, either like the carbon in diamond or the carbon in graphite pencils. Within these samples, every atom that's called carbon has 6 protons. Any atom that has a different number of protons will not be carbon. And this is what we mean when we say that the number of protons helps us identify an atom. The number of protons in any nucleus is not something that we have to guess at. We can look it up very easily. It's such an important value that it is given the name atomic number, and it is represented by the symbol capital Z. If we take a moment and find carbon on the periodic table on the inside front cover of your book, we see two values in this block. The whole number value, usually shown at the top of the box, is the atomic number. If we were to examine gold, we would find that every atom of gold contains 79 protons. The neutron was the last subatomic particle to be identified by scientists. A neutron has no charge, it is electrically neutral, and it has a mass of 1.67493 times 10 to the minus 24th grams. Neutrons are found in the nucleus. The last subatomic particle, and the one that helps us explain a great deal of chemistry, is the electron. An electron is a negatively charged particle with a mass of 9.10938 times 10 to the minus 28th grams. Electrons are in constant motion outside the nucleus. Our current view of the atom then looks like figure 2.9 on page 43 of the textbook. From this figure, we can see that the volume of an atom is occupied by the electrons moving around in essentially empty space. This was demonstrated by Ernst Rutherford in his gold foil experiment, and you can read about that in section 2.2 of the text. The volume of the nucleus, however, is exceedingly small compared to the volume of the overall atom. Let's examine what we know about subatomic particles so far. We know that protons and neutrons are both found in the nucleus. We can see that protons and neutrons have roughly the same mass when rounded to 3 significant figures. The electron, however, is about 1,800 times less massive than protons and neutrons. Notice that the exponent on the electron's mass is 10 to the negative 28th, not negative 24th. This means that when we determine the mass of an atom, the most important particles to consider are the protons and neutrons, or the mass of the nucleus. In fact, the number of protons and neutrons in a nucleus is called the mass number for an atom. For the nucleus that we looked at earlier, the mass number would be 9 because there are a total of 4 protons and 5 neutrons. Mass number is given the symbol capital A in chemistry. It is not a value that's readily available to us from the periodic table. Mass number is the sum total of protons and neutrons that are present in a nucleus. And mass number is the number of the most massive particles. We got to be very careful with our symbolism here. Capital A stands for the mass number, and capital Z stands for atomic number. It's very easy to get these symbols turned around. For every atom, then, we could sit down and draw a picture of the subatomic particles, like this picture of a beryllium atom. Obviously, an image like this is not drawn to scale. It only shows what we know about the number of subatomic particles in a particular atom. But instead of drawing a picture for every atom, it's much easier to use some symbols to specify the atom. A nuclide representation is a collection of symbols that allow us to carefully show what particles are present in an atom. A nuclide representation begins with the 1 or 2 letter abbreviation for an atom. We'll just shorten the abbreviation to X here, and this should be a pretty safe assumption since there's no element X. Imagine a square around that abbreviation. Then, at the corners of the square, we'll give the other pertinent information about the atom. We'll number those corners for the sake of clarity here. At position 1 on the square, we write the atomic number, or Z, for the atom. Remember that this is the number of protons. It's a little redundant to write both the abbreviation and the atomic number, so sometimes you'll see nuclide representations that leave the atomic number out. At position 2 of the square, we show the mass number symbolized with capital A. Again, the mass number is the total of the protons and neutrons. Position 3 tells us the charge and helps us determine the number of electrons that are present in an atom. An atom with no charge shown would have all of the positive and negative charges cancel one another out, leaving an overall charge of 0. In other words, when no charge is shown, the number of protons must equal the number of electrons. Position 4 tells us how many atoms to consider. Let's look at a nuclide representation for a very specific atom of tellurium. We see an atomic number of 52, indicating that this atom has 52 protons. We see a mass number of 128. Since we already know that 52 of these particles are protons, a little subtraction will give us the number of neutrons. Mathematically, we could say that neutrons are equal to mass number minus atomic number. In this case, the neutrons will be 128 minus 52, or 76 neutrons are present in this nucleus. The number of electrons can be determined from the charge. Since no charge is shown, we must assume that the atom is electrically neutral and the number of protons and electrons will be equal. Therefore, this nuclide representation indicates an atom with 52 protons, 76 neutrons, and 52 electrons. In this video, we discussed the similarities and differences between protons, neutrons, and electrons. You should know the charge, relative mass, and location of all these particles within an atom. You should also be able to interpret and write a nuclide representation for any atom. If you're confident that you know these things, please take the electronic assessment in Moodle over this video. You can view the video again if you like, and if you have any questions, please direct them to your instructor.